the end of the last video on integrating a function along a path, we arrived at the formula that you see at the top of the screen. And so if we recall, we said we had the height of that rectangle was f of x of tk star, and then we had the width, which is here represented as a delta sk, which is apparently an integral. So we have an integral, and then we have, so that's the area, and then we have a sum of all n of those pieces, and then we send n to infinity. Not too hard, right? So integral, sum, and limit. Great. Can we make this nicer? And you're like, probably, Professor Bright, if you're asking this question, so let's just get on with it. Before we do that, I want to remind you of something that we talked about way back in Calc 1. So if we had a continuous function, that meant that there was some point in our interval that we were looking on, such that when we looked at the integral, that's the same as saying it's the difference in the bounds times the function at that point. Okay, now how does that help us here? Okay, well, if I look at that s or delta sk, right? According to this theorem, if I use the conclusion, right? So I'm using this part. Okay, well, I have the integral. Can I just say that this is equal to tk minus 1, and then times the length of x prime evaluated at excuse me, tk star star. Okay, now you're like, what is tk star star? And that's just that value c. Okay, so tk star star is just within our interval. Okay, it doesn't necessarily need to be the same as tk star. It could be something different. Okay, well, okay, that's fine and well, but what do we, I guess, how does that help us? Okay, well, why not substitute this in and see what we get? And also just mention here that if we think about this closely enough, this is just change in t on our interval, right? Or in that small partition. Okay? So let's see what we get. We get the limit, of, as n goes to infinity, sum k is equal to 1 to n f of x of tk star, and I'm going to use a double starred just for consistency and notation, delta sk, and this is going to equal, alright, and by the above theorem, limit as n goes to infinity, this whole part doesn't really change, sum k is equal to 1 to n f of x of tk double star. Okay, and then now I'm going to replace that with what I found above. So that first part is delta t, and then x prime of tk star star. Okay, well, now if I rearrange this just a smidge, okay, this is now I don't have an integral inside of a sum. Okay, And so if I no longer have an integral inside of a sum, I think of this, okay, well, this is dt, right? And then the rest, this whole preceding junk, that's the same as an integral symbol. So this is just the integral from whatever bounds I'm on, a to b, that's that partition, right? So I started at a and b and I split it into n pieces, but it's the same as doing the integral. And then there's a dt hanging out at the end. And then the other stuff is just what the function is. So this is f of x of t, and then t star was just a particular point, but now I'm going over all points with the integral symbol, and then I need to multiply this by x prime of t, or the speed, if you will. Okay, so this suffices to say that the whole complicated limit, whatever that we found in the previous video and that we started with here, can actually be reduced using the mean value theorem for integrals to this little expression. And that is actually captured here in this box. Let me just show you, send it back. Okay, so, and what we actually found, we call the scalar line integral for a scalar line integral, and so that's just going to be measuring the area between the path and that function when restricted to the path. And so if we want to find the scalar line integral, so again we have a function that produces a one-dimensional output, there we go. Okay, we found that formula. Okay, and so with that, we're going to go ahead and do a couple quick examples. Okay, all right, so I'll let you pause the video if you need and look at the examples, but we're just going to go ahead and proceed with this. Okay, so I'm going to say integral of f ds, okay, when along this path x. All right, so we're going to be on the domain 0 to 2, and then we're going to do the function composition. So I end up with the square root of 1 plus 4t squared. And then I need to take the magnitude of the derivative of the path, so that would be of 1 comma 2t dt. And if you do your math, I think the square roots end up canceling, so we end up with 0 to 2 of 1 plus 4t squared dt, and you can go ahead and do the math, and I got 38 over 3. Okay. All right, and then just as a second question, so this is kind of an interesting question. I want you to maybe think about the geometry here before we do this. So we have a function and we're given a path. Is there anything interesting about that path? Well, I don't know. And again, we're going to do the math. That's all we're going to do. But I encourage you to think about this geometrically before we actually do it. Okay. So integral of f ds. This is going to be, okay, 0 to pi, and then we have the function restricted to the path. Okay, so cosine squared plus sine squared is 1. That's boring, times and then magnitude. Cosine squared plus sine squared, okay, that's just 1. That's also boring. Dt, so then we just get pi. Huh, that's interesting. So why was this so special? I want you to create an argument and tell me the argument next time we see each other. Okay? So that's all for this video for scalar line integrals. We basically just came up with that equation, or we not came up with the equation, but we derived the equation from our work in the first video and use mean value theorem for integrals to simplify it and make it a little bit more manageable. Okay? Bottom line, take the function times its speed, and then do an integral over the domain for t, and you have your answer. Alright, in the next video we will talk about something closely related to scalar line integrals.